results. Good. You don't need to do the adaptive homework. So let's review quickly. I have reviewed before. Let's review it again. Now you have to know the equations of motion for constant velocity. You have to know the equations of motion for constant acceleration. Okay, and that's how they look like. They become, as you move from constant velocity to constant acceleration, the equations below becomes a little bit more complicated, right? And I even put a table for you. Let's see if I have it here. Comparing those two types of motion. Here you go, uniform motion and accelerated motion. Okay, here is linear, here is linear, right? But then when you go for the positions, the equation is going to be linear in time. But then when we have accelerated motion, it's not linear in time, it's quadratic in time. What you have to know, what else do you have to know? There is one more equation that's very useful for motion under constant acceleration, okay? So those are the three basic equations. And there is one more equation that's very useful. I'll say even two more. There's one more here, right? There's one more equation here for constant acceleration that I didn't put. That's the equation for the average velocity. And then there is one more that you have to know. That's here you go, final velocity plus initial velocity. You saw that before, right? I mentioned that to you before. And V over 2. And then there is one more equation that we obtain from this other two. There is one more, there is one more. There is one more useful equation that you have to know. This equation is derived from the following equations of motion. There's one more equation for, uniformly accelerated motion, right? Uniformly accelerated motion that you have to know. This equation is derived from the following two equations of motion. Okay, here you go. Those two here. Starting with those two equations, we are going to get a third equation that's very useful. Using these two equations, we are going to get another one that is very useful. It's called the Torricelli equation. The equation of Torricelli. So how do you derive that? Okay, we derive this equation by eliminating the variable t. Okay, that's why I bold-faced it. So let me bold-face it here as well. So how do I do that? Well, we do that in the following way. It's just mathematical. There's nothing new about this equation. It's just mathematical manipulation, okay? But it's very useful, this equation. So we start with this first equation for the velocity, and we write t in terms of the other parameter, okay? I didn't do that yet. I pass the V naught to the other side, right? And now I'm going to pass the acceleration to the other side as well. Here you go. Like that. And then what do? I plug this T right in here in this equation, okay? In the second equation to obtain another one. I would say a fifth equation because we already have four, right? We have one equation, a second equation, a third equation, a fourth equation. We're going to get a fifth equation for uniformly accelerated motion. So substitute that in there. Copy and paste it. Go. Good. What you have right here are gonna come right here. And similarly, we're gonna get, okay, we're gonna place our T, our new T in this term. In this term for the position here in the equation. And, you know, I'm just going to repeat the T that you have in there. So I keep track. Okay, and then what I'm going to do, I'm going to expand this equation. V naught is going to multiply V. The V naught here is going to be squared, right? And then I'm going to expand this term as well. It's going to be something like that. I'm going to distribute the power, right? The square power here. The A is going to become squared. Right here. What's the next step? The next step is going to be cancel this A with this other A. And we are going to expand this term as well. It's going to be V squared minus 2V V naught. Oops. 2V V naught. And then there must be a positive sign here. And A square in V naught square. Here you go. Gonna be like that. Now we look at those two terms. You notice that we have, you know, I'm gonna here write that as 2A, right? No, I want to write in the other one. Not yet. Here you go. I'm gonna write 2A here. Oh, not 3A, 2A. Here you go. And we analyze those two terms, we notice that they are very close to each other, with the exception of this number 2, right? That's downstairs. So what do? We put them under a common denominator. Okay, I'm going to put them under a common denominator, and that's what I'm going to do next. Here you go. 2A, when I put it under a common denominator, I have to multiply the top by 2 as well. Divide by 2, multiply by 2. A little trick, mathematical trick that we have. And now they are under a common denominator. Both fractions are under a common denominator. Okay, and once they are under a common denominator, we can see if we can put them under the same fraction, right? Here you go. I'm going to transfer this one to this other, to the other numerator, right? And try to figure out if there are any possible simplifications. Okay, here you go. Try to see if there are any possible simplifications. 2V naught V cancels out with 2V V naught. So this one goes away. Minus 2V naught square plus V naught square. becomes minus V naught square. And we are almost there. Do you see that big equation became smaller, right? And then this equation is usually written in the following way. We pass the x naught to the other side, change the sign of x naught. We commute the V naught square with the V. Okay. And we go the next step. The next step is what? We pass the 2a to the other side. Let's put a parenthesis here. Right here you go. And then we move the V naught square, the minus V naught square to the other side. It becomes plus V naught square. Okay. And we have our Torricelli equation. V square equal to V naught square plus 2a x minus x naught. Well, we can do come up with another simplification here. X minus x naught is what? This delta x, right? That's the equation, that's the new equation you have to know. Okay, and now let's summarize the equations of motion for uniform acceleration again. Uniformly accelerated motion, here you go. I'm gonna add the Torricelli equation to this list. Okay, 1, 2, 3, 4, 5 for constant acceleration. Uniformly accelerated motion, okay. What next we have to do? Okay, so let's do an example, a simple example. And let me take I'm gonna erase this thing that you don't need anymore, right? Here you go. Here you go. Simple example. A real life example, by the way. This is real life example. Okay, so here you go. Real life example is the following. You're driving your car in a freeway at, let's say, 60 miles per hour. 60 miles per hour, okay? And then, you know, and the car just in front of you. Let's see, not the car, let's put another way. And there is an emergency. There is an emergency in the road, and you have to slam your brakes to come to a full stop. Okay, the question is, what is the stopping distance of your car? Let's see here. Let's see. Let's see if we can do that with this one. Let's see here. Let's see. Yeah. And by the way, there is one more equation here that I have to tell you that in reality there are 6 equations. Okay, I didn't mention that to you. Delta x over delta t. Right? There are 2 average velocities. There are 2 equations for average velocity of your car. Okay, this one is a kind of difficult problem. Okay, to solve. Let me. Okay, assume, here you go. Your car, assume that your car is uniformly decelerated throughout this process. Okay. Okay, think about that. How you're going to do it. Okay. You have the initial velocity. Okay. Let's see what we have. You have, you know, what do you know? What do you know? What do you know? 1, initial velocity. Velocity, 60 miles per hour. That we have to convert in meters per second, right? 60 miles per hour, how do you convert that? It's going to be 60 times 1,600 meters divided by 3,600 seconds. Make sense? That's what 60 miles per hour is all about. You do this math and you get the velocity in meters per second. What else do you know? You know the acceleration. The acceleration is uniform. Okay. So from those 2 pieces of information, you can, you can use these 2 pieces of, let's say, from the second piece of information, you know that the motion is uniformly accelerated. Okay. You know that the motion is uniformly accelerated. So you have 6 different equations to play with. Okay. Oh, what else do you have here? There's one more piece of information. Here you go. You're driving your car in a freeway, and there's an emergency road, and you have to, on your brakes, come to a full stop, right? So the initial velocity is 60 miles per hour. Now, let me put here, this guy on the top, okay? Here you go. The acceleration is uniform. The initial velocity is 60 miles per hour. What about the final velocity? Actually, you have 3 pieces of information, right? What's the final velocity of your car? No? Think about this problem. You're driving at 60 miles per hour. Yeah, here you go. It's 0, right? Good, Bethany. Here you go. 0 miles per hour, which ends up being, 0 meters per second. So the key to solve a problem is to find out what is the information that is available, okay? So you have those 3 pieces of information here. Those 3 pieces of information right in here. Okay. So what I want you to do, do that on your own. I'm not going to solve the problem, okay? You can use these 3 pieces of information, right? These 3 pieces of information to solve their problem. That's what we call, the problem of the stopping distance, the stopping distance. So I want you to, I want you to solve this problem on your own, okay? And then next time, we can discuss that again. Okay? Keep that in mind, okay? Simple real life example. So what I want to do now is let us study the problem of free fall. Study the problem of free fall. What's free fall? Free fall. What definition of free fall? Okay. Free fall is motion of an object subjected only to the force of gravity. Okay. Under this circumstance, we know from experimentation that when only the force of gravity is applied, nothing else, right? So let me stop sharing the screen. Here you go. I'm going to give an example, a real life example. Here's an object in my hand, right? At this very moment, we have two forces applied to this object. One of them is the weight of the object that's pulling it towards the center of the earth. Another force that's applied to this object is my hand. The force of my fingers, is preventing the object from moving downwards. This is not, I repeat, it's not free fall motion because we have two forces. If I release the object, then the only force acting in the object is going to be the force of gravity. And that would be considered this type of motion would be considered free fall motion, okay? So what you have to know about free fall motion? You have to know the following about free fall motion. Here you go. Under free fall motion, okay, the acceleration of any, let's see, under free fall motion, under free fall motion, the acceleration of any object is uniform or constant. Uniform / constant. Okay. Constant, okay? And that was this was discovered by Galileo Galilei. Who performed several experiments during his time. Okay, during his time. He also discovered, so he discovered two things. He discovered that acceleration was uniform. He also discovered that the value of the acceleration nearby the Earth's surface was approximately, 10 meters per second squared. That's a very easy number to memorize. It's not exactly 10 meters per second squared. It's a little bit less than that, okay? But we can approximate that to 10 meters per second squared to get just like a 2% missed error in the calculations. The real number is, the real number is 9.8 meters per second squared. Using 10 meters per second square would introduce only a 2% mistake. Okay. Using the approximation would introduce only a 2% error in your calculations, which is, which is acceptable. What's not acceptable is that whenever the error is more than 10%. Okay. So the situation is the following. Here you go. I'm going to illustrate here in my PowerPoint. Here you go. We have, and I'm going to do a real an example. Here you go. Example. Lab notes, lecture note. Okay. Example. Free-fall example. Another one, real life application. Okay, the real life application of free-fall. You are at the top of a building. Okay, and you want to estimate, not to estimate, you want to determine the height of this building. All you have is a small stone and your, let's see, and a timepiece. You release the stone from the top of the building and measure how long it takes for the stone to reach the ground below. Okay, let's say it takes like 5 seconds. You discover if it takes 5 seconds for the stone to reach the ground, what's the height of the building? Okay. Solution. Okay, that's one example. There are several different examples that we can work on. That's just one of them. I like to share that with my students because it's something that can be used in real life to find out the height of a building, right? And what do we do first? Well, first you go ahead and you make a drawing. Every physics problem, you make a drawing. Okay, here you go. I'm going to do little by little drawings here, right? First to the building. In this example, I put 20 seconds, right? First the building, and let's see here. This one right now, and then what do we do next? I put the y-axis. Okay. I put the origin of my y-axis. Oh, what happened here? Step by step. I'm going to take out this one out. Y-axis. Here's the point where the stone or that you're located at the top of the building. Then you're going to get your stone, this little let's see, here. Okay, good. I'm gonna, here you go, put the stone right now at the top of the building. That's what we call the y0 position at time t equal to 0. time t equal to 0. And in the next slide, the stone is about to reach, I'm going to put 5 seconds, okay? Reach the ground, okay? So here you go, play the movie, right? Here you go, the building, the y-axis. That's how you solve problems in physics. You have to do those simple drawings. You know, you set your origin of the origin of your axis. Now I'm going to put one more. Set the origin of your axis first, and then the position of your stone. You know, the position of the stone is right in there at that point. We call that y naught. We do not know what is the height of the building. And that's the position of the stone at time t equal to 0. I said that I release the stone. What does it mean? I release the stone from the top of the building. It means that the initial velocity of the stone is 0. Okay? So you have all those pieces of information that you have to collect before you can solve the problem. Subscript. Here you go. Okay, the stone, you time it, how long it takes for the stone to reach the ground, right? And it takes 5 seconds. G here is the acceleration of gravity. We denote it by G, the acceleration of gravity by G. Should be little g. That's the acceleration of the object. 9:30 something, right? Yeah, 9:35. So here you go. What do you know? Let's write down what you know, right? Going back to the notes here, lecture notes. What do you know? What do you know? 1, you know the initial velocity. Initial velocity. You know, V naught is 0. Two, you know, the motion is uniformly accelerated. Okay. You know that the acceleration is what? 10 meters per second square, approximately 10 meters per second square. I'll put, you know, A is usually denoted by G. You know, for the time of flight of the object, which is 5 seconds. Okay. Those are the 3 pieces of information that you know, the 4 pieces of information that you know. Is there anything else that we know? Free fall, top of the building, the height, and you want to find out the height of the building. So you want to find out why not. So what do we do? Okay. So the equation that we use is going to be, you know, go back to our 5 equations, right? Here you go. 5 equations, 6 equations, 1, 2, 3, 4, 5, 6, right? Here you go. That's our weapons, right? Our weapons that we're going to use, our tools that are going to use to solve the problem. A is equal to G, I already wrote that down, 10 meters per second square. Okay. V naught is 0. V naught is 0. Okay. T, you know, I wrote there as well, is going to be 5 seconds. Right? And the motion is uniformly accelerated, so we are going to need to use those equations that you see right in here. Because the motion is uniformly accelerated along the vertical direction, what do? We change the name of our x to y. Okay, here you go. X become y. Oh, and then there is one more important piece of information that I didn't. So we have 5 pieces of information. One more. Final position of the object, what at t equal to 5 seconds. What's going to be the height of the object at t equal to 5 seconds? Y at t equal to 5 seconds is going to be what? It's going to reach the ground. Here you go. It's about to impact the floor, right? So it's going to be right here. The position of the object at t equal to 5 seconds is going to be 0. Make sense? The key here is to find, all these pieces of information. Okay. So I'm going to put that here, y at t equal to 5 seconds is going to be z0. Okay, so we have our first equation here. Okay, and we can write down in numeric terms. Okay, so here you go. What you have, I'm gonna V naught in this case is going to become 0, right? A in this case, there is a little trick here. Oh, by the way, there's a little trick here. Because, because the acceleration is downwards, okay, and my axis is displayed upwards, then the acceleration should be written in a different way. The acceleration should be is supposed to be written as a minus 10 meters per second square, okay? Minus 10 meters per second square. And that's very intuitive. Why is that? Because it starts at y naught. As the particle goes down, the position keeps on decreasing. The only way that the position is going to decrease is by having a negative value for the acceleration. G is always positive, right? Okay? It's just A that can be positive or negative. So I'm going to fix what I have right in here. Here is, G is going to be 10 meters per second square. I'm going to write that down. A is going to be minus G, that is equal to minus 10 meters per second square. Okay. And then we substitute that right here in this equation, 10 meters per second square, okay, with a negative sign. I will here write that as, okay, that's the equation of motion that we get for the velocity, okay? But we still are not able to solve the problem because we do not know what's the final velocity. We do not know, oh, we do know the instant of time. Yeah, right? We know the instant of time. So we can put 5 seconds here, but we still didn't solve our problem because I don't want to know the final velocity. I want to know the height of the building. I want to know this value right in here, right? But let's finish anyway. Let's finish that anyway. So when I do this calculation here, I find that the final velocity of the stone is 50 meters per second. Okay, the final velocity of the stone is 50 meters per second. Now, remember, I want to find y naught, right? I'm going to put it here. Y naught equal to, that's what I want to find out. So if you want to find y naught, most likely that's going to be the most useful equation for you to solve the problem, right? I didn't ask you to solve the velocity, but it's still a good exercise to see how those equations work. But if you want to find the height of the building, you should be using this equation right in here, right? So let's see where it leads us to. The final position at time t equal to 5 seconds is going to be 0. Why not? We do not know. V naught, we already know that's 0 because the initial velocity, right? The acceleration is minus 10 meters per second squared. Here you go. And t, I told you that is 5 seconds. So here you go. Now let's see if we can solve this problem. It looks like we can solve this problem, right? Because there is no other unknown here in this equation. There is just this single unknown here. So let's continue deriving that. This 10 cancel out with 2, becomes 5, right? Here we're going to square 5, becomes 25. Seconds also is squared, so it becomes 25 seconds squared. And then we get this equation right here. We get this equation right in here. That can be here written as y naught equal to that. The second square cancels out with the second square. We have 5 meters here. And then what we get for that? 125 meters. 125, that's the height of your building. Okay. So we didn't have to use the other equations. We solved our problem without using the other equations. Okay. So I can erase them. Sometimes that's what it takes for you to solve a problem. Okay, you have to try one equation here and another one. I found out of the final velocity, but I didn't have to because I didn't ask for that. And it's just a matter of collecting our equation and figure out which one. So this problem is just a matter of collecting the equation and figure out which one is the most useful. Okay. So that's what we have for free fall. And there is one more thing that I want you to know. That's what we have for free fall. There are other problems on free fall, okay? But that's I cannot cover every possible example because we don't have time to do that. So I need you to look out there in the problems exercise, in the homework, other examples that you may find, okay? To really become familiar with the problem of, not just the problem of free fall, but the problem of uniformly accelerated motion. So what else do we have to know? There is one more thing that I didn't tell you, is how to find delta x and delta v from a graph, okay? You already know that in a x versus t graph, the tangent, the slope of the tangent along the graph is the instantaneous velocity. You already know that. Okay. In a x versus t graph, I discussed that with you. You also know that in a v versus t graph, the slope of the tangent along this graph is the instantaneous what? Acceleration. Okay? A is delta V over delta T, right? There's two more pieces of info, and there are two more pieces of information that you have to know. There are two more pieces of information you have to know. Just recall the definition of average acceleration, right? Or average velocity. Let's go get it here. And average acceleration as well. Let me see, here you go. Average velocity. We start with average velocity here. Okay. And let's not also, we can rearrange this equation in the following way. We can here write that as the average times, oops, delta T. Okay. What does this equation tell us? Okay, this equation tells us the following. This equation tells that when we plot the V against T, okay, suppose you get this complicated type of velocity against time, okay? Okay, when you have a graph like that, the area below this curve is going to be the displacement, okay? Can you memorize that? This thing, you know, becomes more obvious if we come up with a constant velocity graph here, okay? Straight line. Okay, suppose that we have a straight line here. It's possible to prove that mathematically, but requires calculus, okay? So I just want you to memorize. So if you have a graph, a linear graph of velocity against time, right? The area under this curve is going to be equal to delta x. Similarly, if you have a velocity that changes as time goes by, also the area below this curve is going to be delta x. Okay. So let's go back there. Okay. If you plot V versus T, the area under the curve of the graph will be equal to the displacement of the object, displacement delta x of the object. Okay. Similarly, you know, we have a similar result, not for the average velocity, but for the average acceleration. Okay, you got. Similarly, for the acceleration, if you plot A versus T, the area under the curve of the graph will be equal to the change in velocity, delta V, of the object. And how do we illustrate that? We illustrate that in this way. Acceleration in the y-axis, T in the x-axis. You have this, you know, fancy type of curve of acceleration, and what you end up having here, the area under this curve is going to be delta V. Okay, if the, you know, if the acceleration is constant for the special case in which the acceleration is constant. Okay, here we go. Which we have studied, right? We should get a similar result. Here we go. Let's see here. You got the idea, right? It's gonna take me too long to, but let's see here. Let me get this one here. Oh, delta V, right? Okay. So that's the last piece of information that you have to know about uniformly accelerated motion. Any questions about that? Okay. Here, don't forget to have delta T, okay, and this A is equal to delta V over delta T, right? So A times delta T is going, A, right, times delta T is going to be the area of this square, right? And if the acceleration is linear, right, you're going to have something similar as well. So that's what we have for chapter 2. Yeah, that's what we have for chapter 2. And yeah, we can stop here right now. It's almost 10 o'clock. Let's have our 15-minute break, right? And then when you come back, we do our lab meeting. Any questions before we go to the break? If you don't have any questions, we can go for the break from 10 a.m. to 10:15 a.m. When you return, we'll do the level measurements. We will do the lab. Okay. Oh, before you go now, I should have 2 minutes here. Let me take attendance. Yeah, almost forgot that. Sorry. Let's see here. I need not this one. I need the P06 attendance. Today is the 21st. 21st. Neil, are you there, Neil? Don't answer. Okay. Ramirez Arguelles, Maria Arguelles Ramirez. See if I don't. Okay, Maria is not here. Lucy Spitia, are you there? I don't think so. Sonny Khalif, are you there? Julissa Molina. Samuel Sanchez. Okay, so Vanessa, are you there, Vanessa?
Here.
Okay, thank you. And next is McKeon. Are you there, McKeon? Okay, Fisher Dawn. Are you there, Fisher? Okay, I don't hear anything from Fisher. Blessing, are you there? I think I saw Blessing there, didn't I? Let's see here, participants. No, Blessing is not my list. Okay, okay, Blessing is not here. And Janet?
Here.
Thank you. Wendy? Wendy Hernandez. I don't see Wendy in my list either. Next is Ryan Ong.
I'm here.
Okay, thank you, Ryan. Mia Villalobos.
I'm here, Professor.
Thank you, Mia. Raymond Garcia. Thank you, Raymond. Next is Donovan Harris. I don't think Donovan is here. No. Joshua Jimenez.
I'm here, Professor.
Thank you. Luis Latiza.
I'm here, Professor.
Thank you. Lily. Thank you.
I'm here, Professor.
Thank you. Michael. Michael Hasid, right? Okay, thank you. Okay, thank you, Ryan. Daisy Mariscal.
Professor Fisher said he's here.
Who is that?
Last name Fisher. This is Lily, but in the post, Fisher said he's in class.
Okay, Lily, right?
Yes.
Okay, good. And Daisy is here too, right?
Yes, I'm here, Professor.
Okay, Donia.
Here.
Thank you. Next is Ana Lopez. Ana Gabriela Lopez. Thank you. Mary Okek.
I'm here, Professor.
Thank you. Jennifer Perez.
I'm here.
Thank you. Elika Lafay.
Here, Professor.
Thank you. Bethany.
I'm here.
Next, Arthur Pacheco.
I'm here.
Thank you. Brianna Valencia.
I'm here.
Next, Pedro Ruiz. Let's see, Pedro, are you there, Pedro? I don't see Pedro here. Next, Basilio Lopez. Okay, good, thank you, Basilio. Next, Vahar.
Here.
Thank you, Alejandra Marmolejo.
I'm here.
Thank you, Alejandra. Amarilis. Are you there, Amarilis?
Yeah.
Okay, thank you. Justena, Yusef.
Here, Professor.
Thank you. Yesenia Montes Rodriguez.
Here.
Thank you. Labelud. Good. Next is Lydia.
Here.
Next is Jade. Are you there, Jade? I don't see Jade here. Next, Ashley Diaz.
I'm here.
Okay, Erica Fajardo.
I'm here.
Okay, good. So, okay, 28. And if you're not called, let me know. Okay. And let's go. Okay, let's go for our break now.
Sir, I'm here right now.
Who is that?
This is Fisher.
Fisher. Which group are you, Fisher?
Group 1.
Group 1. Fisher. Okay, here you go. Thank you. Anybody else? Blessing, are you there? Don't see Blessing. Wendy. I don't see Wendy. Donovan, Jade. Okay, so now let's extend our break a little bit more, right? 10:05 to 10:20. So I see you in 15 minutes. I'm back here. Keen. Okay. Okay, so he go. Okay, now. Let's talk about the exam, right? Because that's the big one that's coming. Yeah, I won't, like I said, I won't be able to postpone the exam, right? Because we have this holiday, this Jewish holidays that won't allow us to have the exam until further down in the calendar. So let's see, where is the, yeah, here you go. That's what I want to cover here for you. Let me just rephrase what I told you about the exam. Okay, for the first exam. Right? So yeah, we're gonna have homework 1, chapter 1, section 1.3, chapter 2, and then I'm not going to burden you with homework 3 this time, okay? Otherwise, it's gonna be too much for us to cover on Monday. So let's concentrate for the first exam only this thing and lab, the ideas, and lab 1 as well, including CL, right? That would be the material for this first exam. We leave chapter, we leave vectors for the second exam. But we'll be covering it vectors next Monday. But then, because Monday is just 2 days before the exam, it's better that I don't include. I'm not going to include vectors. I am not going to include vectors in exam 1. Okay, I'm not. Good. So first exam is still scheduled for September 28th. Good. And now, and don't forget lab 1, graphs, all those things about graphs that we learned, right? And now we can start talking about today's lab. Let's see. Actually, lab notes. Let's see here. Okay. Today is the 21st. So last time I provided you with data documenting the diameter of 6 different spheres. Okay. So make sure you have this data there. Downloaded the file from your group folder. Okay. And I want to make sure everybody has a group, right? If you don't have a group, let me know. Okay, here you go. That's group 1. That's group 2. Right? That's group 3. 4. 5. Okay. 6. Pedro Ruiz, are you there, Pedro Ruiz? 7, 8, and 9. Okay, so go ahead. You should have your spreadsheet already in your hard drive. Okay, and what we have there in that spreadsheet? Let's take a look at one of those spreadsheets that I downloaded for you. Let's see here. I want to go here. Google Drive. $2022. Oh, I'm gonna get so your spreadsheet looks just like that. Okay. The first thing that you have to do is to document the density of steel in kilograms per cubic meter. That's the first thing you have to do. Go in the internet and type it. Gotta make sure you type the value in there. Okay. So go in the internet, and we did that before, right? And find the value, the density value of the steel, the density of steel, and document it in your spreadsheet. When it comes to the spreadsheet, when it comes to the spreadsheet, please do not change anything. Do not change the format of the spreadsheet, okay? Do not add the lines nor columns. Okay, do not change the position. Please do not change the position of the tables. I will be using that specific format to grade your spreadsheet. And if you go to your spreadsheet, there is this first table here that you gotta get the density of steel, and then there is this second table here. In the second table, you have data for the measurement of the ruler, using the ruler, right, to measure the diameter of 6 different spheres. Okay, and let me quickly go through that right here. So here you go. Here's your ruler, right? Your ruler looks just like that. It's just a small section of the ruler. I have a ruler here, but I broke it. Okay, let me show you one of my rulers, my broken ruler. A little piece of it. What a shame. Here you go. Do you see my ruler here? It was longer, but I broke it. The other piece of the ruler is somewhere else here. But you have, those numbers along the rules that in this case, tells you the centimeter, right? The value of the length in centimeter. But some rulers, they do, instead, they show the measurements in millimeters as well. Just like this one here. In this case here, we have 5 millimeters, 10 millimeters, that's 1 centimeter, 15 millimeters, and so on. Okay, what else you have to know about the ruler? Okay, you have to know that the ruler has this smallest division here. Okay, the smallest division of an instrument is called the resolution of the instrument. Let's write it down. The smallest the smallest division of an instrument is called resolution. In the case of the ruler, the smallest division is going to be 1 millimeter. Okay, and you have to keep that in mind when you report the measurement of the measurements that you make with your ruler. Okay, so because the ruler has because the smallest division of the ruler is 1 millimeter, comma, you must report your measurement according to this resolution. The smallest division is slash resolution. You must report your measurement according to this resolution, okay? So if you have, for instance, let me give you an example, okay? Out of that spreadsheet right here. In this specific case, notice that the measurement of the diameter of the sphere number 2 was reported as being 0.014, okay? Which is 1.4 centimeters. Let's go there. Let's go back to my, okay. In the case of a sphere of 1.4 centimeter diameter, if you were to report this diameter, this value, this diameter that was made with the ruler, comma, it should be incorrect to report it as 1.40 centimeters. You cannot do that. Okay, it'd be incorrect to report it. Why is that? Okay, the reason being due to the fact that you are, is when you write something like that, okay, the fact that when you write something like that, okay, you are stating that your instrument has a resolution better than 1 millimeter, okay? So if you were to report 1.4 centimeters there, let's not forget, we are going to report that as, you know, in meter. You should write that down as 0.014 meter. You know, do not put a 0 there. If it's the ruler, you know, should be 0.14 meters. You know, it would be incorrect. It would be incorrect to report it as 0.0140. It should also be incorrect. It would also be incorrect. Would also be incorrect to report it as 0.01 meters. Okay. Would also be incorrect to drop this last figure. That's the whole principle, you know, that is the whole principle of significant figures. The whole principle of significant figures. You cannot report too many figures, but you cannot report too few figures either. You have to report your measurement. You have to report your measurement according to the resolution of your instrument. Okay, you must report. So in this case here, I'm going to do this just one example. Okay, in this case here, if you're going to report, don't forget you already have the units here. You gotta put the units there at the top. You don't put the units. You don't carry the units here in the cell. Okay, in the cell you report only the actual number. So in this specific case, what do you have to do? You have to change the format of your number. You're gonna put a number there and adjust the number of decimal places until you have the correct number of decimal places. In the case of the ruler, because the resolution is 1 millimeter or a thousandth of a meter, you have to go all the way down to the third decimal place only for the ruler. Okay. Let me change that. And then you will have to change the format. So, okay, in the case, lab notes. In the case of the ruler, you report your measurement as being X point, X meter, where X is are your numeric values there. Okay. I am going only up to the 1,000 decimal place. To the 1,000 decimal place. Is that clear? Okay. Now let's take a look here at my ruler, right? I have my ruler here. That's how the ruler looks like. And then I'm gonna measure the diameter of this sphere. And the funny thing about the ruler is that it's a little bit difficult to measure diameters of spheres, okay? Because you have to eyeball it. But it's not because of you have to eyeball it that's gonna be giving you the incorrect value. It may give you a pretty good value of the diameter. What I mean by eyeball is you have to eyeball where one edge of the sphere starts and where the other edge of the sphere starts, okay? And that's, turn out to be rather inconvenient, may introduce some errors, okay? But it's not because it introduced some errors that you're going to throw away your measurement. No, you still use it. But to remove this inconvenience, okay, people developed a different type of instrument, a different type of measuring instrument, which is called the vernier caliper. The vernier caliper looks just like that, okay? It is a fancy rule, is a ruler that has two jaws here. If you want to measure the diameter of a sphere, for instance, all you have to do is to open this jaw and fit the sphere inside it. Okay? Makes sense? People invented this type of device. And what I want to do here, I want you to concentrate for now just on the scale that shows the zero, okay? Don't worry about the other scale that follow up. So what we have here is just a fancy ruler that allows you to make more precise measurements of spherical objects, for instance. In this specific case, the diameter of this sphere would be what? 1, 2, 3, 4, 5, 6, 7 millimeters plus something else. Okay? That's how we would measure the diameter of this sphere with the vernier caliper, which is, by the way, is just a fancy type of ruler. If you go, so right now we have this measurement that states that the diameter of this sphere is 7 millimeters plus something else that I do not know what this something else is. You can either eyeball it, estimate with your eye what this something else is. This is small differences, right? Take a look here. See, we have a small difference here. The zero is this zero here that's telling you what the diameter of the sphere is. But we do not know what these small differences. Okay, in order to find out what this small difference is, people came up with a very smart invention. Okay, that's shown right in here. Here is my ruler. without the sphere there inside. Okay, notice that we have this second scale right here. We have the main scale, that is just a regular ruler. And then you have the second scale that we call the vernier scale. Okay, the vernier caliper, you go. The vernier caliper is another device capable of measuring the lengths of objects in a more convenient fashion. Okay, convenient and accurate fashion. Note that the vernier caliper has two scales. The main scale, that is just a ruler, and the vernier scale that allows you to measure an object up to a tenth of a millimeter. That's the resolution of the vernier caliper. Okay, and I'm going to teach you how to measure this, how to use this vernier caliper, this vernier scale right here. Any questions so far? Okay. So because the vernier caliper has this resolution of a tenth of a millimeter, okay, the measurement in the case of the vernier caliper, the measurement must be reported with an additional decimal place, or x.xxx, another one here. Everything in meters, a tenth of a millimeter. Okay. There are, you can see illustrations of vernier calipers out there. Those are real devices. Here, I'm just illustrating more or less how it looks like. Okay, notice that this vernier scale also has 10 divisions. Okay, you can count 10 divisions. 1, 2, 3, 4. 1, 2, 3. Wait a minute. 1, 2, 3, 4. Ah, no, I made a mistake here. 1, 2, 3, 4, 5. I picked that up, huh? Let me fix that. Ungroup. Nobody knows that. Here you go. It's going to be something like that. Let's see how I'm going to do it. Say such with there, and this one too is not good. So let me see. Let me fix that. I have 10 divisions from here to here, right? So the vernier, this vernier scale should have, 1, 2, 3, 4, 2, 3, 4, 5. Let's move it. Here we go. Okay. Yeah, and so here you go. Now I should have it right. That's how the vernier scale should be displayed. The vernier, right here. Okay, so here you go. Now we have it right. See, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 divisions. And those 10 divisions are 9 millimeters long. Do you picture what's happening here? It is this small particularity that allows you to come up with a resolution that is a tenth of a millimeter. Without this vernier scale, you cannot come up with this a tenth of a millimeter resolution, okay? So here you go. So if you are measuring the sphere with this scale here, 1, 2, 3, 4, 5. Okay, this one is good shape, right? Yeah, this one is in good shape. What would end up being this measurement? Well, let me show you how. You go ahead and you lined up the 0 with the upper scale, you get 7 millimeters, 5, 6, 7 millimeters. Okay. And then you look at which one of those lines lined up with the division upwards. Okay. In this specific case, the one that's precisely lined up with the one at the top is the fourth one. So in this specific case, your measurement is going to be reported as 7.4 millimeters. Make sense? Okay. Let me show you some pictures of vernier calipers out there in the internet. Let's see here. Is the vernier caliper supposed to have 3? What do we mean 3 ms? I don't understand, Daisy. 3. You mean did you mean what? 3 millimeters? 3 meters? What did you mean? In the notes it said point. That's no. It's just 1 it's just 1 m. Where did I put 3 m's? Let me check here. Where did I put them? Here in the notes. Where did I put that? Well, it's supposed to be just not 3 m's, okay? Oh yeah, here you go. This one, that's an incorrect. Thank you for picking that up. Okay. Vernier caliper is smallest division is 0.1 millimeters. Okay. So you report your measurement, right? As being, here is going to be, x meter, right? Here is going to be x meter. And let me show you a picture of a vernier caliper, a real live vernier caliper. Okay, here's one of it's a metallic one, a metal vernier caliper. This one is being sold by, let's see, $50 more or less. That's in reals, in Brazilian currency. Okay, divided by 5 is like around $50, $60. That's how they look like. Okay, this one is even more fancy than the other one that I drew there because it has far more, the vernier scale has far more divisions than mine. Okay, we don't use this type of vernier caliper there in the college. Okay, so it has a better resolution. Let me see another one. It's not as fancy as this one. Oh, the brochure. Let's see. Definition diagram. Let's take a look here. Okay. Here the vernier scale of a vernier caliper. Okay. Again, this vernier scale here is fancier than the other one that I showed to you. Let's see. But that's how those vernier calipers look like. The regular ruler, those 2 jaws that are used to clamp the object and measure diameters and other types of lines, okay? So that's what you have to know. And then you finally have the micrometer. The micrometer is another device that we use in the classroom, and it has a resolution that's even better than the resolution of the vernier caliper. So one more decimal place here is 1/100th of a millimeter. Okay, I'm gonna put it here, line them up. So that's how you should report your measurements there in the spreadsheet. For the ruler, up to the 3rd place in the meter. For the vernier caliper, up to the 4th decimal place. And for the micrometer, up to the 5th decimal place. Let me show you the micrometer. The micrometer, we have unfortunately, I don't have any of those instruments here with me, otherwise I would be showing you. Okay, that's how the micrometer looks like. Okay. And we even have a simulation of a micrometer that I can show to you. Micrometer simulation. Micrometer simulation. Okay, let's see here. Virtual micrometer, hundreds of millimeters. Stuff must be okay. Here you go. This one here. So go ahead, get a link for displays and practice measurements with the micrometer. Let me send that to you all. Here you go. Link. Of a simulation for micrometer simulator. Okay, so here you go. Let's see, we can click it that. I like this. This one, let's see here. Visual micrometer simulator. Oh yeah, here you go. Right in here. Let me blow it up. Okay. That's how the micrometer looks like. It has, let me move a little bit further away. It has the regular ruler, right? Right in here on the top. Every millimeter, right? Then we have this other secondary ruler that's 1/2 of a millimeter. So here is 0 millimeters, 1/2 of a millimeter, 1, 1.5, 2, 2.5, 3, 4, 5, right? So you have those 2 scales. And on the type of that, you have this 3rd scale here, this 3rd rotating scale. Okay. So you can fit your sphere right here between the jaws of this micrometer and take a measurement of the diameter of the device, right? In this specific case, how we'll take the measurement, okay? If you, let me see here, no, stop it, okay. In this specific case here, what's gonna be the measurement that this micrometer is taking? Okay, it's gonna be like 10 millimeters from here to here. To see this edge here of the rotating scale is just past 10 millimeters. 10 millimeters plus something else. Okay, this something else is going to be given by which one is lined up with the horizontal scale. Which line of your rotating scale is lined up with the horizontal line of the main scale, okay? So in this specific case, how you're gonna report? You're going to report 10.10 millimeters, okay? You can see here, here you go, 10.10 millimeters, that's the result of the measurement. Notice that he's reporting only up to the second decimal place in millimeters. And in this case, well, how many significant figures are going to have? We're going to have 1, 2, 3, 4 significant figures. If it's your ruler doing the measurement, you'd be reporting only 2 significant figures for this measurement. If you're the vernier caliper, you'd be reporting only 3 significant figures for this measurement. Okay. So for a given, let's write that down here. Okay. For a given measurement obtained, let a given measurement obtained with the micrometer be 10.10 millimeters. Okay, in this case, there are only 4 significant figures. In this case, there are 4, not only, but 4 significant figures in this measurement. So you count that 1, 2, 3, 4. Because you are using a micrometer, it would be incorrect to report this measurement as 10.100 millimeters. Okay, incorrect. I'm gonna bold-face that. This same measurement should be reported, right? Be reported by the vernier caliper as 10.1 millimeter. And that's because of the resolution of the caliper. Similarly, the ruler would report the same measurement as 10 millimeters only, In this case, would be 3 significant figures and 2 sig figs. Okay. Which, by the way, I will write that down, 0.0101 meters, which, by the way, would be equal to 0.010 meters. Okay, and here 0.01010 meters for significant figures. So now you should be able to report the proper number of significant figures on those 3 columns. Let's work on that. Let us work on that, and then we can work the rest. Okay, let's go one by one here. 21st, 31 students. Okay, we have 30 here. Good. I'm going to ask you how you're doing there, Vanessa. Did you download your Excel spreadsheet, Vanessa?
Yes, I did.
Good. So now I need you to report the proper number of significant figures for the ruler, for the vernier caliper, and the micrometer. Okay, do you know how to do that?
Yes.
Okay. So again, let's go through that, right? If you're going to report the proper number of significant figures, what do you have to do? For the ruler, you gotta click the cell, right-click the cell, format cell, change your your category from scientific to regular number, and put, because we're dealing with the ruler, you know, and put like display 3 decimal places there. Okay, that would be the right way of reporting the number of significant figures there. Any zeros to the left of a significant digit is not a significant digit. Okay, so here you go. I'm going to write that down here for you. Any zeros to the left of any zeros to the left of the leftmost significant digit is not a significant digit. However, any zeros between or to the right, between significant digits, or to the right of the rightmost significant digit are considered significant digit. However, any zeros between significant digits or to the right of the rightmost are considered significant digits. Okay, that's the rule that we have for significant digits. So go ahead, you know. Here's the table that I have here for you is an example, okay? Resolution for the ruler of 1 millimeter, resolution of the vernier caliper at 10ths of a millimeter, resolution of the micrometer 100th of a millimeter. A measurement that's 12 millimeters. Now, how do you report with the ruler? You report it as being 2 significant digits only. For the vernier caliper, you report it as being having 3 significant digits. And the micrometer, you report it having 4 significant digits. And that's how I abbreviate, you know, the significant digits here with X's. Here you go. And here's in meter, here's in millimeter. Don't forget, everything here in your table must be reported in terms of meter. All the units goes here in this horizontal line, okay? Don't forget to fill up the unit. You start with those 3 first, and then we worry about the others. We measure the lengths, and then we also measure the mass of the sphere. Why are we doing that? We're doing that for a very good reason. We want to find out the density of those spheres, okay? I provide 6 different spheres to my students during the lab. They measure the diameter of the sphere with 3 different instruments. They make a table, this table that you see right in here. The table calculates the volume for you of those devices, and they also measure the mass of the spheres. So let's see how we are progressing there. Let's see, I'm gonna go for group number 2. Ryan, are you in good shape there, Ryan? Do you have the Excel spreadsheet there?
Yeah, I have the spreadsheet. I'm just, you know, working on it.
Yeah. So at this point in time, what I want you to do, not just work on the not only on the significant digits, but work also on the units, right?
Yeah.
Okay, so I need you to fill up the units right here. And the proper number of significant digits here on those 3 columns. 1105, we have another. Let's take a quick break, right? Otherwise we're gonna get burned out here. 1105 right now. And Okay. Let us have a break. Let us have a break till 11:20 a.m. Okay. And then I'll talk to you more about the other measurements that we have in there and how we perform this lab. I'm back here. So at this point in time, what we have talked about, we have 40 minutes to go. Let's try to cover everything that we can, right? So what we talked about so far, we talked about the ruler, the vernier caliper, we talk about the following instruments, the ruler, the vernier caliper, and the micrometer. Okay, we also covered the concept, a very useful one, of significant figures, and how we are supposed to report a measurement. The number of significant figures of an instrument depends on its resolution, or the smallest division in the instrument. Okay, so that's what we talked about. Okay. The first step in a measurement is to report its proper number of significant figures. Okay.
Professor, I think you forgot to share your screen.
Oh, thank you. Thank you. Every now and then I forget to do that. Okay, thank you. Okay, so here you go. Talk about the following instruments: the ruler, the vernier caliper, and the micrometer. We also cover the concept of sequence figures and how we are supposed to report a measurement. The number of sequence figures of an instrument depends on its resolution or the smallest division in the instrument. The first step in a measurement is to report its proper number of sequence figures. Okay. Now we did that for the ruler, for the vernier caliper, and the micrometer. Okay. Now in this experiment, in addition of measuring the diameter of the spheres of the sphere, we also measured their mass. Okay, last column in the second table. Take a look at the last column in the second table that you have right in there. Okay, so here you go. Those are all measurements. Measurement made with the ruler, measurement made with the vernier caliper, measurement made with the micrometer. And also, we performed another measurement. This measurement we measure the mass of each of the spheres with the scale. Okay? To measure the mass of the spheres, to measure the mass of the spheres, we used a scale an electronic scale. Okay. This electronic, and you have to know the resolution of the electronic scale. This electronic scale, I have to tell you, okay? If you are doing that in the lab, you could see directly in the scale, in the measurement there of the scale, what would be the resolution of the scale. But here, because we're doing this make-believe experiments, right? I have to tell you what the resolution, okay? The resolution of this electronic scale, the resolution of this electronic scale is what? Well, 0.01 grams, okay? That's the type of resolution that we have for this scale, which whenever converted in the main SI unit for the mass, we have to add 3 more decimal places and report the unit as being kilograms, okay? That's the resolution of your electronic scale. Consequently, any measurement, any mass measurement with the electronic scale must be reported as x dot, let's put capital X, x dash dot x kilograms. Okay, reported as. So going back, we have measurements of diameter and measurements of mass. Since you are supposed to report as the proper number of significance figures here, you're supposed to report all the way up to the 5th decimal place. Okay. In this specific case, it's going to be, you go, like that for this specific measurement. Okay. Don't forget the unit here is kilogram. Don't forget to put the units here. We're not ready yet to put the unit here because I didn't tell you about volume, right? If here we have a measurement, here we do not have measurements. Here we have results that are obtained from measurements. Okay. Makes sense. That's how the logic goes. Let's see here. Okay, and the result that we're going to get in there is the result for the volume of the sphere. Okay, the volume of a sphere can be written down as the 4/3 pi r cubed. But don't forget, the radius is half the diameter. We did not measure the radius with the ruler. We did not measure the radius with the vernier caliper. It's very difficult to measure the radius with those instruments. It's not easy. Instead, we measure the diameter. So we must here write this equation in terms of the diameter, which ends up being 1/6 of pi d cubed. Diameter to the cube. Okay, this formula is already programmed in my spreadsheet. If you go right here and click in any of those cells, you're going to see that I wrote down the formula here for the volume of the sphere. 4/3 pi diameter divided by 2 to the cube. Okay, so the moment that my students write down the diameter of the sphere, my spreadsheet already automatically calculates the volume. Okay. Here you must report the proper number of significant figures. Here you must also report the proper number of significant figures. But those are measurements. And you already know what the rule is, right? The rule for reporting a measurement is by reporting up to the resolution of the instrument. That's how you report the number of sequence figures of a measurement, right? I'm going to write that down here for you. Here you go. To report, just to emphasize here, right? To report a given measurement, you must report to the decimal, up to the decimal place of the resolution of your device, of your instrument. Okay, to report the significant figures, okay, the significant figures of a given measurement, you must report up to the decimal place of the resolution of your instrument. To report the significant figure of a result, not measurement, you must know the equation that relates the measurement with the result, right? With the result. The result in this case, is the volume of the sphere. And very soon you're gonna understand why we're doing the volume, why we're working on the volume and not the area. Okay. And the equation for the volume is given by this equation right here. Now the question is, how do I report the proper number of significant figures of the volume? Okay. Okay, the rule that's adopted out there, okay, rule for multiplication and division, okay? This rule applies to multiplication and division. How, the number of significant figures of a given result. Okay, I wrote down just specifically for the volume, but I'm gonna write down for the most generic type of result. The number of significant figures of a given result will be the list of number of significant figures in your measurement, okay? In the case of the volume depends only on the diameter of the sphere. So there is no other measurement involved here in this volume. So what you have to do, you have to report the number of significant figures of your diameter. Okay? Remember, if the number of significant figures is not the number of decimals, okay? Remember, number of significant figures is not the same as the number of decimal places, right? Students usually confuse that one with the other. So you go ahead. At this point in time, you should already formatted your measurements according to the right number of significant figures. You're gonna go here, let's say, this example here, right? Format cell, I'm going to report to the right number of significant figures, which is the third decimal place in meters. You count the number of significant figures here. How many significant figures do we have here? We have only 2 significant figures here, because zeros to the left of significant figure is not a significant figure. This volume is calculated in terms of this measurement, okay? So if this measurement has 2 significant figures, this volume must also be reported with 2 significant figures, okay? Because this number here is less than 1,000, here you go. If I'm going to report it with 2 significant figures only, right? And I'm going to put it as a number in the number format. Let's see how many decimal places do we have to add to see 2 significant figures there, right? So here you go, 1 significant digit. Follow the number right in here. Do you see that? That number that's reported right here in the cell. When I start changing the decimal places, the actual number is going to show up here in this region here of Excel. Okay, with one decimal place, I still see zeros there. With 2 decimal places, I still see zeros there. I have no significant figures. 3 decimal places, 0 significant figures, because all the numbers here are 0, right? 4, 5. Well, we are going to start seeing significant figures now at the 6th decimal place. Okay? At the 6th decimal place, we finally see our first significant digit. And remember, I want 2 significant digits there, right? So I have to add 1 more decimal place. That's how your volume must be reported in Excel. 2 significant digits here, 2 significant digits here. Okay? Everybody understand that? You gotta do that for everything else. And then for the caliper, it's going to be 3 significant digits. For the micrometer, it's going to be 4 significant digits, okay? And so the volume for the caliper and the volume for the micrometer will have like 3 and 4 significant digits. So that's the rule. Since we have just 1 measurement there in the volume, you use the number of significant figures of that measurement, of the sole measurement. If you had 2 measurements there in your result, like an area, right? Area, you have 1 length times another length, you know, your area would have to be reported in terms of the least number of significant figures. You're going to have, you know, the area is going to be would be given by 1 measurement times another measurement, right? Whichever has the least number of significant figures is what should be reported in the area, for the number of significant figures of the area. Okay. So let me undo what I did here. What else you gotta do? Here you go. Let me go back what we had there before. Notice that's very cumbersome to report. To report this number with a bunch of zeros, right? You see, it's very difficult to read something like that that has so many zeros before the number here. It's very cumbersome. So we have this rule, right? If you have something like that, you don't report as a number. You report as in powers of 10. That's what we call scientific format. To report it in powers of 10, don't forget to keep the same number of second digits. Just go there in that cell, right-click it, format cell, and go back to the original format, that scientific rule, scientific format. And make sure you report the number with the right number of second digits, right? In this case, you're going to have only one decimal place. And the number that are being reported, the number that's being reported here has only 2 second figures, right? 4 is 1 second figure, 8 is the other second figure. That would be the right way of reporting the volume measured by the ruler. It's much easier to read something like that than to read something else that has a bunch of zeros in there. Okay? So what's the rule that I like to adopt for the scientific format? Okay, let me write that down here, a nice rule. In general, you should any number less than 10 to minus 3 and greater than 10 to the third power must be reported. Let's not say must, let's say should be reported in scientific format. Scientific format. And what scientific format? Powers of 10. Okay. So let's adopt these rules throughout the semester so it makes to make it easier to read any measurement and any result that we display there. Okay. I'm going to revert. Okay. Yeah, here you go. Now that's the okay, 11:40. We have 20 more minutes to go. So we cover significant figures. Okay, so what did we do? Here you go. That's the rule that I mentioned. Okay, we cover. Here you go. Summary. Density value of steel, significant digits for measurements, diameter and mass, significant digits for the volume, which is for a result. Significant digits of a result. In this case, the volume. And now you have to report the units of diameter, the units of volume, and the units of mass. Okay, now doing dimensional analysis like we covered before, what's going to be the unit for the volume, right? Everything is being reported in meters for the diameter. Okay, when we calculate the volume here, you have to cube the diameter. When you cube the diameter, not only you take the cube of the numeric value, but you also take the cube of the unit itself. If the unit here is meter, the unit for the volume is going to be what? Cubic meters. Okay? That's what we have for significant digits. Let's see here. Any questions? Now we're going to go to the actual experiment. This is just an introduction what you have to do for every experiment that we perform. Okay? You have to worry about the units. You have to worry about the significant digits. You have to worry about the proper format. The format can be regular numbers or can be scientific format numbers. Numbers in scientific format. Okay, and now what we're going to do? Well, we're going to find out what is the density that those students measure, that what the density value of those spheres from our actual measurement. We already know from the table, from the internet, the density of the steel. Now, the question is, do we get the same density from those measurements that we made here? And if we do, how do you obtain the density of those spheres, right? One way to do that, is the better way of doing it, because it uses statistical ideas, okay? Is by referring to the equation that you see right here for the mass and the volumes. You see that here? That's the relation that's the relation for the density. The density is mass divided by volume. We measured the mass, we calculated the volume. Okay? Because we use spheres of same material, then which is steel, then we should expect each of those 6 spheres to have the same density. Then what do? We here write our formula in the following way. We write that in terms of the mass. Mass is density times volume. Density is the same for every sphere that we use. So consequently, this value here should be a constant, no matter what the sphere that we have. And what we do next? We plot M in the y-axis and the volume V in the x-axis. That's what we do. That's what you have to do now. Here you go. Plot M in the y-axis. I'm going to do that with you, right? Start for the ruler. Here you go. Mass, highlight the mass, highlight the volume. Make sure you know how to do that. There's a little trick here. If you can't get the plot, let me know. Insert chart. Here you go. We get a plot. Does it look like a straight line? It looks like a straight line, right? Because it looks like a straight line, the slope of this line should be very close to the density of steel. Going back to the formula, to the equation that you saw right in here. Okay, so here you go. Mass in the y-axis, volume in the x-axis. Here's the slope of your equation. Do you see that?
Hey, Professor, could you show again how you highlighted both of them?
Oh yeah, that's a little trick, right? Let me write this thing here first, and I'll show you how to do that.
Okay.
Okay, so here you go. Like that, right? Mass is the y-axis, volume in the x-axis, and the density is the slope of your straight line, okay? So let's do that again. That's the little secret that I struggled to learn when I didn't know that, when I was learning Excel. Who was able to plot the graph? Anybody was able to plot the graph? Maybe some of you already know how to do that, huh? Anybody is gonna?
I got it.
You got it? How do you do that?
You hold down control, like you highlight the
Yeah.
left-hand side and hold control to get the other one.
That's right. You highlight the first one, hold the control key, right? And highlight the second one. Okay. In the Mac is different, right? In the Mac, you hold the command key, right? Whoever has a Mac should be holding the command key. If the other one is next, right? You don't have to hold the control key. All you have to do is to click and drag both columns simultaneously. But if they are separated, then you have to use the control key, right? So here you go, highlight, highlight, insert, right? Then you do what we did at the beginning, right? You're going to put the trend line there. Here you go. Trend line. Here you go, linear. Set display equation on chart and display R square on chart as well. Note, see, folks, that this is actual real life data, okay? Note, see that R squared is not equal to 1 because this is real life data. And then we have this slope here that should be very close to the density of steel, right? 8,948. Let's see if it's close enough. Density of steel in kilograms per cubic meter. Density of steel, yeah. So ZUR, yeah, we're getting more than a little bit more than the maximum value here, right? But that's okay. Okay, you take the average of those two. Let's see, you get 7,750, we get 300 difference, right? 100, you sum with 150, you get 7,900. That's what I should write for my density of steel, writing here in my spreadsheet, 7,900. Oh. 7,900. And then if I log 8,948 here in the other table, right, this slope, see that? 8,948. We end up getting a percentage difference that is what? Let's see, what's the percentage difference here? I'm getting a 13% difference. Okay, 13% difference, 13.27% difference. And don't forget to put the unit here. Unit of the slope, unit of the percentage difference. Not bad, right? That's because it's the ruler, and the ruler is very difficult to measure the diameter of a sphere with the ruler. Okay, so let me. So that's what you're going to keep on doing throughout the semester. You're going to keep on plotting graphs like that. Let me undo everything. Okay, so 11:50, we have 10 more minutes to go. Okay. I want you to finish all of that. Don't forget plot. So let's put a list here of things to do, right? Let's see here. Report 6 figures of the measurements. 2, report display, right? Not report, display the proper significant figures of the measurements. In this case, 3 diameters and 1 mass. Okay, what else? Display the proper number of significant figures not of the measurement, but of the results. You know, three different sets of volumes, no? 3 different sets of volumes. Okay. Display, write down the units in their proper cell. The units in their proper cell. Okay. Plot M versus V for the ruler, vernier caliper, and micrometer. Okay. Obtain, display the regression equation and the R² value. Okay. What else you have to do? write down the slope of your regression equation in table. What's the table number? In table, let's see, that's 02, 03, in table 04. In table 0-4. Okay. Check the percentage difference. Okay, everything in red, every quantity in red do not require significant. You don't have to report. You don't have to report the number of significant figures for quantities in red. Okay, so here you go. So here you go. We have the slope that's in red, percentage difference in red. You don't have to worry about significant figures here. You don't have to worry about significant figures here either. Okay. And here is the number of data points. It's going to be 6 for everyone. What you see here is the regression equation. Regression equation for the ruler, regression equation for vernier caliper, regression equation for the micrometer. And then the CL, right? Lower and upper bounds of CL. For the ruler, for the vernier caliper, for the micrometer. We are coming to an end here, and any questions? Let me go through some of you folks. I won't be able to call everybody, right? But at least one person per group. Let's see, Joshua, are you there, Joshua?
Yes, I'm here, Professor.
Okay, were you able to do everything that I covered?
Yeah, I have one quick question. So on the first on table 0-2, so you know how all the units they're in scientific notation, are we supposed to change them to numbers, or do we leave them like that?
You mean here?
Yeah, like that table, are we supposed to leave it in scientific notation, or we're
No.
supposed to change it?
No, this one, let me see something. Yeah, this one you put as a regular number.
Mm-hmm.
What you put in scientific notation is this one here.
All right, sounds good then.
Because they are less than 10 to minus 3. See that?
Mm-hmm.
They are less than 10 to minus 3. So you change that. This one, yeah, this one you leave as a number as well. Number and number. Anything less than 10 to minus 3, you put in scientific notation. Okay.
That sounds good. Thank you.
Less than 10 to minus 3, greater. Did you plot the graph too, Joshua?
Yes, I was able to plot the graph.
Okay, good. And then you can do the rest at home, right? Here you go, the CL and blah, 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 right? And what's very important here is the percentage difference. Well, we usually get less than 10%. The lower the percentage difference, the closer is your experimental results to the theoretical results. So in those experiments, we usually get less than 10%. Sometimes we get 13%, 15%, and but those are rare instances that you're gonna get like more than 10%. Okay. Let's see, anybody else here? Joshua, I talked to Joshua. Let's say Daisy. Are you there, Daisy?
Yes, I'm here, Professor.
Okay, did you follow everything? Do you have any questions?
Yeah, I followed everything. For table 3, we're following the formula to get the number, correct?
Let me see, table 3. Are you talking about this table here?
Yes.
Okay, here you go. Here you use the number of data points, right? So that's 6.
Mm-hmm.
6, 6, and 6. Are you asking about this one here?
Yes.
Okay, yeah, this one is the regression equation, right? Whatever regression equation you found for the ruler, you type it here.
Okay.
Whatever regression equation you get for the vernier caliper, you type it here and so on. R square is straightforward, right?
Yes, it's from the graph.
Okay.
Okay. Got it.
Yeah, and here is from the table that I gave to you, right? And
Okay.
we came up with a. Okay, let's see, one more. We are running out of time. 2 more minutes to go. So now you are ready to prepare the lab report for me, okay? And do work on the spreadsheet and turn in the spreadsheet next Wednesday, please. You know what? Let's see. Now, next Wednesday is going to be the lab, the exam. Okay, here you go. You don't need to turn in next time, okay? Lab report. Report for this lab, do 2 weeks from now, okay? Report for this lab, do 2 weeks from now, okay? Since you're gonna have exam next week, I can give you 1 more week of break here. Yeah, I'm gonna do that right now, Bethany. Any more questions? 11:59, just 1 more minute to go. We'll save it as a PDF. Is it 1 lab? Yeah, 1 lab report per group, Janet. 1 lab report per group. And at this point in time, just turn in the spreadsheet, okay? Just turn in the spreadsheet. Only the spreadsheet. Next time I will ask you more than that. This time, let's see, lab notes. Where's lab notes? Okay. Turning only the spreadsheet. Next time, I will ask you for more. Okay. Nothing is due today until 2 weeks. That's right. That's right. Okay, and then I will save that in this PDF format. Okay, so it's 12 noon already. If you don't have any questions, we can, finish now, and I will see you Monday. Yeah. Lab notes. Let me stop sharing here. Lab notes. Notes.
Professor,
Yes.
Yeah, can you go back to the Excel sheet? That's all right.
Which one? Which Excel sheet? The lab?
Yes.
Okay. So which who is talking? Who is that?
It's LAHC.
Vag. Okay. Let's see here. I'm gonna share the screen with you. Here you go. That's the Excel spreadsheet.
Yeah, so for the first part, where we right click and then you said format, we changed the number from scientific, yeah, to regular. So
Yeah.
we don't have the same Excel as, well, I don't, as the same one you have on screen.
That's right.
So, so for example, when I click on, I can like right click, when I click on format, and so here, let me just do it. I press like format, and it just goes to numbers. It says number, percent, and then scientific for me. I know you said don't do scientific, but how would I do it for the updated Excel version?
You go number, right? Click number.
Just
Do,
number.
do, 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 do you see the same window when you right click it?
No, it's not the same one because this is an older version.
Okay.
So it's a different thing. Like my format is much different than the one yours is.
I see. Is that a Mac or a Windows computer?
It's Mac.
Okay, Mac. Yeah, Mac also has a different display there. So you have to figure out which one, it's going to be slightly different, but all you have to do is highlight number. I think, I think the Mac is going to show number in there.
Okay.
Right. It shows scientific, right? It shows number. What else? It shows percentage there.
Yeah. It says just number, percent, scientific. I know we just press number. That's it, right?
Yeah, that's right. And then adjust the decimal places, right? Don't forget to adjust the decimal places.
Okay, and then for the exam, do we need to also look at anything in the book, any concepts that we haven't gone over in notes, or just anything that we just went over with you is fine?
Only that what I cover.
Okay.
Only what I cover.
Okay. All right. Thank you. That's all I needed.
Okay. Okay, so any more questions? Okay, if there's no more question, I'm going to terminate here the meeting, okay? And I'll see you on Monday.
Professor, since I'm not going to be in class on Monday, or Michael, can you email us what happened on class after, and then we could check on Wednesday?
Yeah,
So
I will upload the notes in the Google Drive. Check the Google Drive. Okay, every time that we finish the class, I am uploading the notes there in Google Drive. Okay.
Okay, thank you so much.
You see?